Okay, so let's start. Well, I'm Javier Galván. I'm a pre-doctoral student here at the IFISC, and I am performing my PhD studies under the supervision of Claudio Mirazo, Jose Ramasco, and both Franz Scher and Wolfgang Maas from the University of Graz. So in this talk, I'm going to present a little bit what is predictive coding and the main results we have obtained already in our investigation. For that purpose, we are going to see what is this thing that we call predictive coding. We are going to present the main characteristics of the primary visual cortex. What are the most recent experiment results within these studies? We are going to present our results, and we are going to discuss a brief ideas. So, what is predictive coding? What if I told you that we can predict our future? That we do it all the time, and we do it quite well. We are experts at it. You look a little bit skeptical about this. What is going to happen next? It is easy for us to predict what it is going to happen next in this image. But it isn't that easy, in fact, because you must know about gravitational movements, fluid dynamics, social interaction, about pranks, understand. You basically give some context to the situation that you are seeing in this image. You can even feel the water running through your back. And we do this all the time. You may know with which word I'm going to enter, I'm going to finish this. It is easy for us to predict the future. For example, consider when you are talking with a friend. You try to predict how would you feel if something similar happens to you. This means that you are making predictions all the time, just making simulations of the different futures that could happen. But if we are trying to predict the future all the time, doesn't this interfere with what we are receiving, with the stimulus that we are receiving from the surroundings, from what we see, what we hear, what we feel? They do. Consider, for example, color. Gray shirt, black jeans. No one would ever disagree with that. No one would ever, too many persons would ever disagree with the color of clothes. But they do. Many of you may know this image. Many people see that this image is compounded by two colors, gold and white. And other people think that this image is composed by blue and black. But what these people, the difference between these two people is just the considerations that they are making, the predictions that they are making on the lighting conditions of the image. And I'm going to prove this to you. Consider two different stripes of this image. They are the same stripe. To the first stripe, we're going to surround it with a certain context, particularly an autumn image. And the other stripe, we are going to put a spring lighting image. So you can see that now this appears to be gold and white, and theirs appears to be black and blue. So the point is that we don't have a direct interaction with the surroundings. We make predictions, and these predictions interfere with what we receive from the surroundings. This is what we call perception. Perception is basically the comparison between what we predict to hear, to see, to feel, and what is actually there. And there is a balance between the predictions and the sensory input. This is really interesting because if some people have a higher and more weight in their predictions are stronger compared to what they receive, they will see things that aren't there, hear things that aren't there, hear voices, put intentions in other people that aren't really there. This is what we call schizophrenia. Also, other people may, this is what we call autism, sorry. And other people may have a lot of sensory input compared to their weak predictions. So the surroundings will look for them unpredictable, and they will try to reproduce patterns of behavior just to gain a little bit of predictability on the precinct. This is what we call schizophrenia, and the other one was autism. But predictive coding is really useful. It allows us to determine where a car will go through and prevent us from suffering an accident, for example. And an interesting case where the predictions that we make appear are visual illusions. Consider, for example, when you are in bed at midnight and you wake up a little bit and you see your chair with all the clothes and you think that it is a thief that has just entered your house. That is a visual illusion. So your predictions are wrong in these cases. So according to this theory of predictive coding, we have two different types of input in our brain. The ones called bottom-up input and the top-down input. The bottom-up input talks about the sensory information we receive. Consider, for example, this case. We are going to talk only about the visual input. This is a pilot coming from a plane. Many of you, maybe all of you, I don't know, haven't seen many of these. So the image just enters to you. You cannot make any predictions or considerations about this image because you don't have a previous concept about this, a previous context about this situation. The top-down input talks about the contextual information and the predictions we make. They take into account the experience, the attention, all the spatial information, the movement. For example, a simple example will be this cube. This is a 2D image, but according to your experience, you can make some predictions about the 3D projection of the image, the 3D reconstruction. Okay, so how does the brain do this kind of computation? Well, according to the literature, across the different parts of the cortex, there exist several layers. Particularly, the layers 2, 3 is supposed to make some kind of subtractive mechanism between both the top-down input and the visual input. Consider, for example, in this case, this neuron, this excitatory neuron, receives inhibition from the top-down input and receives excitation from the bottom-up input. So different neurons make different calculations. Some of them subtract both inputs in one direction and the other in the other way around. Okay, so as I said before, we are going to focus on the visual inputs. Particularly, we are going to present the primary visual cortex. This part of the brain is located in the occipital lobe, and it's present in both hemispheres. It receives the visual stimuli that comes through the eye, and which goes through an intermediate point, which is in the thalamus, and it is called lateral geniculate nucleus. And the visual input, with the visual information, goes through the eye via the optic nerve to this part. From this part, it is sent through many innervations to the primary visual cortex, sometimes called also striate cortex, which we are going to call B1. Related to this, a couple years ago, well, the last year, the group from Ville present a really accurate model about the primary visual cortex of the mouse. Many different models have been proposed along the years, but this is the last one that has been proposed and the more accurate one. This model has in total 51,000 neurons divided in different layers. In each layer, except from the first one, we have one class of excitatory neurons and 3 classes of inhibitory neurons. each class presents different models. So here you can see a representation of 1% of the neurons in the model, divided in the consequent layers. So what we do is just take this model, implement it on TensorFlow, so we have right now a neural network that we can train and we can play with it. As I said, it has 50,000 neurons, nearly 52,000 neurons, and it's based on many different experimental data that has been get from the literature. The Allen Institute, which is the institution that published this model, have a lot of data on different experiments on mice. Particularly in each layer, we can see that there is a balance between excitatory and inhibitory neurons of 85-15%. And these models have been trained to reproduce spike trains in different validation experiments. Many of them consider like drifting gratings, that the one seen in the image. And this image is converted into spikes through the lateral geniculate nucleus model that we have. And these different spikes send currents to the different neurons in the model. So we're going to see now some experiments that have been done to explore this predictive coding mechanism. One of the first ones was this, published by Keller, by the group of Keller in Neuron in 2012. They had several mice coupled to a treadmill, a spherical treadmill, and surrounded by a visual artificial reality, which shows like drifting gratings. So basically, they are trying to make the mouse think that he's running through a corridor, and the gratings represent like the walls in the corridor. They measured the activity of these excitatory neurons from layer 2 and 3 in the primary visual cortex. And here in this simulation, you can see how the experiment worked. Particularly, in this case, the mice movement is coupled to the movement, to the speed of the gratings. And at some points, they stopped the image, but let the mouse to keep on running. This is making an error. The mouse is running, so he expects to see the bars going backwards, but they aren't. So we are generating a wrong prediction in the mouse, which should appear, should reflect some activity in the excitatory neurons from layer 2-3, according to the literature. Here, you can see also, this is the part of the neurons of the primary visual cortex in this experiment. You can see the activity. This bar reflects the speed at which the mouse is running. And when the red square here appears, it means that they are stopping the image. They are generating at that point this error, these prediction errors. Seems that it don't want to work. Okay, don't worry. Focus, for example, in the neuron that it is within the red square, the red box. It fires when there is an error, a prediction. When the visual stimuli stops, it fires. So that neuron will be a candidate for being computing this kind of error in the prediction. Okay, just to illustrate you what we expect to happen in these experiments, consider this simple example. Consider that a mice running through a corridor, and at the end of the corridor, it turned left, and it sees an image. When it sees the image, the activity in this layer should rise up because he didn't expect that. But we can continue to reproduce this experiment in the same mice, so it will start to expect that image to appear at the end of the corridor. So if we reproduce this experiment many times, we will see that there is an increase in the activity before it turns left, so it is the mice is expecting the image to be there, and the response after it turns left will decrease because it finds what it expects. So what could happen if we remove the image from the experiment? So the mice will run through the corridor, it will turn left, and it will find nothing. What we expect to find, what we will find in this case, is that there will be an increase in the activity according to the prediction, but a higher increase in the activity will be seen when the mice turn left and finds nothing, because this means that the mice is making a wrong prediction about what he will find. Last year, the group of Keller also published this paper with new experimental results. Particularly, they make two kinds of experiment, which we will call closed loop experiment and open loop experiment. With closed loop experiment, what we are referring to is that the visual flow speed is coupled with the locomotion. This is exactly what you see in the animation of the mice running through the treadmill. At some points, we will stop the image, which translates into zero speed visual flow. And they tracked how 32 different neurons from the excitatory, 32 different excitatory neurons from layer 2 and 3, how they respond to this mismatch, what they called. So you can see here two different examples. The first example relates to a neuron that depolarized as an effect, as a response to this mismatch. Notice, for example, how the activity, the voltage, the membrane voltage, rise up at this point. And in the other case, this is what we call an HMM neuron, and DMM neuron, a neuron that depolarizes. And in this other experiment, in this other neuron, we find the opposite, that the activity decreases with the mismatch. This neuron is what we call an HMM neuron. And here you can see the average behavior of these neurons. Here they are presenting the voltage. Or for example here, also the voltage of the different neurons. In the upper part, the neurons that depolarize, you can see that there is an increase in the voltage response during the mismatch, and some neurons that hyperpolarize. They also find that this activity was correlated with the speed of locomotion. The higher, the fastest the mice was running, the higher the response of these neurons, for both the neurons that depolarize and the neurons that hyperpolarize. They also performed a second experiment, which is the open loop experiment. In this case, they let the mice run freely, and at some random points, they let the gratings to drift at a certain speed, which is higher than the locomotion speed. Hence, they are making the other kind of error, an error where the expected visual flow is lower than what they see, than the visual flow they receive. In this case, they tracked the same neurons that they labeled in the previous experiment, but now they find the opposite, that the neurons that previously depolarize now hyperpolarize. You can see that in the blue, with the blue colors. And the neurons that hyperpolarize now depolarize as a response to this experiment. Here you can see the average behavior of the two populations of neurons. Okay. So they also tracked some neurons from deeper layers. Particularly, these are neurons from layers 5 and 6. And they see that this kind of reverse behavior doesn't appear in these neurons. So they conclude that this split in HMM and DMM neurons, hyperpolarizing and depolarizing neurons, was characteristic from neurons from layer 2 and 3. Okay, so now that we have all this experimental data and results, we are going to see if our model, the model that we implemented from the Ville group, from the Allen Institute, is able to reproduce these results. So we took our model and we present the following experiment. We don't have the locomotion input, but we will only present the model the visual input. This translates into something like a 0 locomotion input, since we don't have that. So we present the model, 1 second drifting gratings image. After that, 1.5 seconds of the stop image, then again 1 second of the drifting gratings, then again the halt, the stop gratings, and so on. Along these studies, we will see the results of different experiments in which we will change both the orientation of the gratings and the speed at which they move. Particularly here you can see the response of the neurons from the lateral geniculate nucleus, the intermediate point before reaching the primary visual cortex, how they respond to the different gratings. Here you can see, for example, the instantaneous firing rate of these two neurons, of these units, 2 units are from the lateral geniculate nucleus, which are indeed the same. This is for a 2 hertz stimuli, and you can see the 2 peaks, it is correlated, and here for a 6 hertz stimuli. So we record many things, but to start with, we record these spikes. We labeled each neuron spikes in time, and here we represent the spikes of the neurons from the thalamus, from the lateral geniculate nucleus, and also the spikes from the neurons from the different layers in the primary visual cortex. This is in particularly to a static gratings frame. This means that we only show the image and keep that image over the 2.5 seconds of the experiment. Then we switch to 2 hertz drifting gratings. This means that for the first 0.5 seconds, the model was shown an static image. Then for 1 second, a drifting gratings video of 2 hertz frequency, and then again a 1 second static image. And now you can see a more clear response of both the neurons in the lateral geniculate nucleus and neurons in the primary visual cortex. Also, here you can see for the 6 hertz drifting gratings, the activity has increased. So there is a correlation between the activity of these neurons and the speed of the visual input. So I said that we are tracking many different variables in the model. Particularly, we are tracking spikes, which you have just seen. We are tracking the membrane potential and the input currents each neuron receives, which we split in 3 different components. The external current, which takes into account the current that it is provenient from the lateral geniculate nucleus. The recurrent current, which comes from other neurons within the B1, within the primary visual cortex. And the after spike current, which is a little correction that we won't care much about in this experiment. You can see that its value are really low. Here you can see how the different values, different variables distribute during the phase of the static image. So we use these values, these mean values, to normalize the different variables and to be able to see how the different variables respond to the movement of the gratings. So we wanted to perform or to see if there is a splitting in the behavior of the excitatory neurons from layer 2 and 3. So we used the total input current to say whether a given neuron was depolarizing or hyperpolarizing. Particularly, we say that a neuron depolarized, which we called HMM, if its average input current during the stimuli was greater than 0.2 picoamperes, and we say that it hyperpolarizes, which we call DMM, if it was lower than minus 0.2. If it was between, we call them unclassified neurons. And some interesting things, we can already find some interesting differences between these two kinds of neurons. We see that when the movement starts, the neurons that hyperpolarize receive a lot of recurrent current, which may be provenient from inhibitory neurons in the network. And that the neurons that depolarize receive little to none recurrent excitatory current, but receive a lot of external current from the lateral geniculate nucleus. So it seems that the external input is driving the depolarization of this neuron and the hyperpolarization of the other ones. Okay, so here we represent 10 neurons from each class, and we present the average currents they are receiving. We see that the neurons that hyperpolarize, what we just see before, are receiving a lot of inhibition from the rest of the network, and that the neurons that depolarize are receiving a lot of excitation, which results in this balance. These neurons are hyperpolarized, these neurons are depolarized. But interestingly, this image that we have obtained, these results, are quite similar to the experimental results from Keller. They see that some neurons hyperpolarize and that their voltage is going down, is decreasing, and the ones that depolarize, the voltage is increasing. We are obtaining the same results, but with the input current, because the membrane voltage wasn't a reliable variable in our model. Okay, so at this point, we have found that we can reproduce this behavior that Keller reported, this splitting in two different kinds of neurons. So the first thing we might ask if this behavior is transient, which means that if we let the stimulus send excitatory input to the network for a really long period of time, this splitting might disappear, and all the neurons will behave in the same way. So we perform this different experiment where the visual part with the drifting grating part will be longer, of 7.5 seconds, and every 0.2 seconds we make a classification of the neurons and count the number of neurons of each class. And we see that the number of neurons for each class doesn't seem to decrease in time, which means that this is a permanent state of the network. So the next point would be to try to explain what are the mechanisms driving to this splitting. So first of all, we look for the in-degrees distribution of these two kinds of neurons. Here you can see the in degree with respect to the other neurons in the primary visual cortex, and here the weighted in degree, where we are taking into account the different weight of the connection of the synapses. And you can see that the neurons that hyperpolarize are more connected. They show a larger degree but their connections are weaker. But more interestingly than this is to explore the different degrees with respect to the inputs they are receiving from the thalamus. Particularly the neurons that hyperpolarize, many of them aren't receiving nothing from the thalamus. They are disconnected from the thalamus. And the neurons that depolarize are connected with it. They show larger in degrees and weighted in degrees. So this may allow us to explain some of the features of these two types of neurons. The next thing we did was to see this in degrees, divide this in degrees and weighted in degrees with all the different neuron classes, and to explore the different type of connection these two neurons have. And we find that the neurons that depolarize receive much more excitatory input from excitatory neurons from layer 4 than the DMM neurons. Also, the DMM neurons receive larger inhibition, particularly from layer 2, 3. So now, up to now, we have two main possible explanations for our splitting behavior. The first one will be the excitation that these neurons are receiving compared to these ones, also with the inhibition. And that the HMM neurons, the neurons that depolarize, are receiving much more input from the thalamus. So now that we have labeled all the excitatory neurons from this layer, we can see how they respond to different stimulus. Particularly, the first stimulus that we proposed was the inverse to the previous one. We present a moving image, then we stop it, and then we move it again. And we see that during this period, the neurons that hyperpolarized in the previous experiment now depolarized, and inversely, which is exactly what Keller found in the other experiment. He found that the neurons that he labeled as DMM depolarize, which is the same that we found, and the neurons that hyperpolarize also hyperpolarize within this experiment. So in order to keep on exploring the different features that might affect this splitting, we performed this second experiment. We change the speed of the stimulus. Now the stimulus will be running at 6 Hertz. And we see that those neurons that were labeled as DMM still depolarize out with the same that we find with the experiment at 2 Hertz. And the neurons that depolarize continue to depolarize. Which the main characteristic, the main qualitative change that we can observe is the frequency that can be seen in the input currents they are receiving. So we can also classify the excitatory neurons from this layer according to this new experiment, and see if both labels, the one from the previous experiment and the one from this, match. And we find that 95% neurons that were classified as DMM according to the first experiment are still classified as DMM according to this one. So the neurons' behavior, the same happens for the HMM neurons. So the important thing is to extract from this confusion matrix is that the neuron's behavior, qualitative behavior, hasn't changed with respect to the speed of the gratings. So another feature that could affect the behavior of the neurons could be the orientation. For that purpose, we made this second experiment in which we presented gratings that drifted vertically to drifted in a vertical direction. And we find that the behavior of the neurons has changed. It isn't as clear as before. So we again made a new classification according to this stimulus, and we find that it doesn't correlate with the previous experiment. So the behavior of the neurons has changed with the orientation of the stimuli. Finally, we want to see if these neurons are affected by the direction of movement. So we present the same experiment, but now moving to the right, and we see that the neurons that at the beginning hyperpolarize still hyperpolarize, and the neurons that depolarize still depolarize. And you can see it here. The classification still remains quite valid. So the neurons aren't much affected by the direction. So another thing we want to explore are the inhibitory neurons from layer 2-3. We want to know if these neurons also present a splitting on two different type of neurons, or if they doesn't. And if they do, why? So we performed the same experiment, classifying both types of neurons according to their input currents, and we find that there was a single type of neurons, the neurons that depolarize. Others remain unclassified, but non-inhibitory neuron from this layer hyperpolarize due to the stimulus. And more interestingly, these neurons that depolarize are depolarized because of the recurrent currents they are receiving, not because of the external. The external input hasn't changed nearly at all. So we explore the connections of these neurons, and we see that they are basically receiving excitatory input from the layer 2 and 3, which are the neurons that we were labeling before, the HMN, the DMN, and the unclassified neurons. So those neurons are driving the excitation of this layer. So up to this point, the main things that we have observed is that our model showed this splitting between the two types of neurons, the ones that depolarize and the ones that hyperpolarize, as in the experiments from Keller. Also, that the characteristics of the stimulus plays a key role. We change the orientation, we change the speed, and some things change in the network. The neurons that depolarize start to hyperpolarize, and vice versa. Also, that the recurrent connections might be important, because remember that the HMM neurons, the neurons that depolarize, have stronger connections in the network, and the neurons that hyperpolarize have lower to none connections with the thalamus. So one interesting thing is that, according to the model, each neuron is associated with a preferred angle of the orientation of the movement. So we try to see if there is something in these three kinds of excitatory neurons that determines their behavior. And we find that the neurons that depolarize have preferred orientation for the horizontal lines, from the lines with 0 degrees and the lines with 180 and obviously 360 because it's 0. And the neurons that unclassified have preferences for the drifting gratings in perpendicular directions to this. To directions in 90 degrees, which were the perpendicular, and also to directions going down. But interestingly, the neurons that hyperpolarize seem to have no preference, no angle preference. Also, another interesting feature is that the neurons, here we present the probability of connection. And we find that neurons of the same class have a higher probability of connection than neurons of other classes. And here we present the mean input weights of the different neurons. And we see that the same, that the neurons that from the same classes have stronger connections within them. Notice that both matrices are symmetric, and this means that the neurons from the different classes are forming clusters. They are associating basically or more strongly within them. So before explaining the proposed mechanism for this phenomena, I wanted to present a brief concept, which is competition through common inhibition. Consider two populations of excitatory neurons, each of them with the recurrent connections, and both of them connected to a population of inhibitory neurons. So we can introduce some excitatory input to both neurons or to any of them, and we see that when we introduce excitatory current here, this activates the inhibitory neurons, which sends inhibition back here, but also sends inhibition here. So depolarizing these neurons, introducing excitation in these neurons, drives inhibition in these neurons. You can see it here. Here, we are introducing excitation in these neurons. And you see that after some time, they start to present higher activity, and the others start to present lower activity. And the other way around. If we present more stimuli, more excitation to these ones, the other ones will start to calm down. So, putting all this together, we can present the following mechanism that can explain what is happening in our network. Here is the mechanism proposed by the experimental people from Keller. They say that this is the visual flow input, this is the bottom-up input. Forget about this one. Focus on the visual flow one. They say that the visual flow, this excitatory input, might activate some inhibitory neurons that hyperpolarize the HMM neurons. And that this excitation, this visual flow input, might excitate some neurons directly, which are what we call HMM neurons. And what we found is nearly this, but not exactly. This will be a subtractive mechanism, but we find something more similar to a competition through common inhibition. We found that the DMM neurons were connected within themselves, strongly than with other groups, but they receive very little to none excitation from the visual input. And the neurons that depolarize receive larger excitation from the bottom-up input. And the neurons that were unclassified receive little because they don't like this direction of motion. So, since we see that the inhibitory neurons from layers 2-3 mainly connect and nearly exclusively connect to neurons from layer 2-3, excitatory neurons of layers 2 and 3, they are excitated because of the neurons that depolarize. The neurons that prefer this direction activate because of the visual stimulus, activate and send current to the neurons, inhibitory neurons, whose activity increases. As we see, they always increase their activity, sending inhibition to the three types of neurons. We find that for the neurons that remain unclassified, there is a balance between these inhibitory currents and the excitatory currents they are receiving, so their behavior remains the same. But for the neurons that hyperpolarize, they are receiving this inhibition and they are receiving nearly non-excitation, so they hyperpolarize. And for the neurons that depolarize, there is a balance between the excitation they receive and the inhibition they receive. So due to the excitation they are receiving from the thalamus, they result into depolarization. So basically these neurons are hyperpolarizing because of the relation of this, the activation of this, with the inhibitory neurons of the same layer. So to conclude, we have seen that this behavior of two types of neuron splits through all the neurons from layer 2 to 3. That the bottom-up and the top-down inputs play a key role in this separation. But if we only have the visual input, which is our case, we can also see this splitting. So the top-down input may just enhance this effect. Also, it remains unclear how this computation it is done. We have proposed a different mechanism, but up to this point it is not clear, and more study needs to be done. And as we proposed, a possible explanation for this effect might be related with computation through common inhibition. So to conclude, I present the following idea, which will be targeted in the following months, I think. This is the same scheme that we see before, but we have proposed how the locomotion input could enter the network. This locomotion input could target mainly, but not only, the neurons that were hyperpolarizing due to the stimulus. And now we will have these neurons will excitate due to this input, and will excitate the inhibitory neurons. And now we will have a direct competition through common inhibition, where the inputs, the locomotion inputs and the visual inputs will be compared through this mechanism. But this is only an idea I really want to explore in the subsequent months of my investigation. So these are the references, and thank you for your attention. I don't know if there are any questions here or in the Zoom or in the YouTube. I don't know how this works right now. Yeah, Miguel.
I have two questions, but I was wondering during all the talk if you were planning to include the locomotion input.
Yeah, right? We want to.
My other question is, well, perhaps it's kind of a dumb question because I'm not too deep in the neural networks. But
go ahead.
When you presented the reverse input and the perpendicular input,
yeah.
Well, in order to define a reverse or perpendicular, the network was previously trained in some way. I mean, if you expect a different answer when the strikes are traveling in the opposite direction, this is because in some way you have to find what is the normal input. So this kind of a previous training for the network, so you can.
The network was trained by these people from the Allen Institute, and they assigned each neuron a preferred direction.
Okay.
So it was expectable that this could happen, but I didn't know in which way. So yeah, we wanted to explore this, and yeah, it is mainly because of the preferred directions each neuron has.
So it's kind of a topological
yeah.
feature.
Yeah, exactly. You're welcome. Okay, I don't know if. Yeah, go ahead. Yeah.
Maybe some background on the neurophysiology of the brain. Interesting. This remind me of the classical work of the visceral. That there are neurons specialized in one or horizontal line, vertical line.
Yeah.
So in this case, the full approach changes a little bit because the bottom up is to be rewired in the brain. You already go
Yeah.
The hypothesis of predictive coding has this, it's not so specific. You don't need that the sensory input is codified by specialized neurons from the start. And this is something to take into account if you want to propose a different mechanism or different than just subtraction. Because with this experiment, you have this different element, which is specialized neuron.
That's right.
The difficult question is how the movement of the mind matter for the equation, for the prediction, and how your model tries to grasp the movement of not the brain, but the system where the brain forms up.
Yeah, to continue unveiling these predictive coding mechanisms, it is necessary and compulsory, and we will do it in the next ones to figure out how to include this top-down input and this locomotion-related input. So yeah, we cannot be sure what it is happening without this input, but for us it is interesting that with only visual input we can see that this splitting appears.
The splitting doesn't let you say that this is an error signal.
Yeah, I know. It is a response to the preferred angles of the network. Yeah.
The coding account
Yeah.
were committed that some of this activity has to be interpreted as an error signal computation. I'm expecting horizontal line, and it's not coming on the horizontal line, then some neuron should fire. That would be something that what you propose is quite different. It's very interesting, but maybe more. You will have to address all this.
Yeah, I know. I have time. Yes, Claudio.
I fully agree with you, Tony, that the fact that we have to take the neurons that depends on that we take the angle is only because we're using the visual system. But if we go to the auditory circuit or other cortical circuit, that wouldn't be necessary. We feel or we believe that this behavior is independent of this specification of the neuron. That it would happen because we think, or at least I think, that this is a competition between external and internal cortex. That under certain input give rise to this separation between HMM and DMM. And you are right that this is not an error correction computation, but as far as I understand, Heather says that this separation in HMM and DMM is essential to do the subtraction between, or at least it happens during the
mismatch.
The error.
Yeah.
Measure, or during the error prediction.
Focus on horizontal and vertical lines.
No, that's.
There is not much that the expectation, that the prediction can play here.
No.
You can induce an expectation by movement. But then in the analysis this is not very sure.
Yeah, I think that the fact that our concentration is, or we're concentrating in the fact that we can separate neurons in HMM and DMM. And this seems to be, there is a quite very new experiment which is not published yet, which is in archive, where they show that they don't need the locomotor input to prove that you can have the two types of neurons. It is not published yet, so we don't know. The experiment is not exactly the same as Keller's one. It's slightly different, but what is claimed is that to have this separation between these two types of neurons, you don't need to have the motor input. And this is what we are getting as well. This separation, which doesn't mean that we are computing any error here, because we don't have the input. We can only separate between these two neurons. It's not necessary, the motor part is not necessary. However, as you said, then if you want to compute an error, then you need to include both. And I think that the mechanism that Javier has proposed is very interesting because this is something we can only do in the experiment. You cannot do this in the simulation. You cannot do this in the experiment. You cannot measure all these currents, everything. So if the model is good enough, you can understand more than we have understood up to now in the experiment.
That's it.
Focused on conflict also between, it was in attention, in the area of psychology of attention, to try to explain how the winner gets all in the end.
Exactly.
It was not exactly the same, but there were reciprocal unilateral inhibition neural network to explain how the perception shows up unique even at some point that it could be ambiguity or several something. In the first example you showed constancy of color.
Yeah.
So it really could really
Yes, send us a paper.
Yeah.
Because we are not aware of it.
Okay.
it also read Lorente de No. You never heard of Lorente de No? Okay. Lorente de No was a Spaniard that worked in the States for 50 years in Rockefeller University. Was a disciple of Veronica Farah. And was the first to see that the organization of the brain, of the cortex, was columnar.
Mm.
It's a standard. It's that you have layers of neurons that this is the
Okay.
one that had the idea, and that's what the
Okay. Yeah. Thank you. Okay. Time to have lunch.
Thank you very much for your class.
¿Te mola? Ay, curro. Él dice que no, pero yo sí.
Ahí, batería.
A ver si... Ya esto está para publicar. A ver si lo publicamos ya de una vez. El problema es eso, la parte del bottom up. O sea, sí.